In this video, we will discuss the geographic coordinate system. In this Cartesian plane, the location of the green point is denoted by 2, 3. That means this point is located at 2 units in x direction and 3 units in y direction. Similarly, when we want to locate a place on Earth, we use the geographic coordinate system that uses a 3-dimensional spherical surface to define location on the Earth. A location is referenced by its latitude and longitude values. Latitude and longitudes are angles measured from the Earth's center to a point on the Earth's surface. The angles often are measured in degrees. In the geographic coordinate system, horizontal lines or east-west lines are lines of equal latitude or parallels. The line of latitude midway between the poles is called the equator. It defines the line of zero latitude. It divides the Earth into northern and southern hemispheres. The latitude degree increases from equator to North Pole and decreases from equator to South Pole. Plus 90 degrees is the latitude at the North Pole and minus 90 degrees is the latitude at the South Pole. Vertical lines or north-south lines are lines of equal longitude or meridians. The line of zero longitude is called the prime meridian. For most geographic coordinate system, prime meridian is the longitude that passes through Greenwich, England. It divides Earth into the Western Hemisphere and Eastern Hemisphere. The purple line passes through Italy and its longitude is 12.5 east of the prime meridian, while this purple line passes through Baja California and its longitude is 115 degrees west of the prime meridian. The origin of geographic coordinate system is at the intersection of the equator and prime meridian. So, to locate a point or any object on the globe, we need latitude and longitude of the location. This is just like the Cartesian plane we saw earlier, where we need x and y coordinate to locate a point. Latitude values are y and longitude values are x in the geographic coordinate system. Latitude and longitude values are traditionally expressed either in decimal degrees or in degree, minute, second. Now we will talk about the shape of the Earth. We know that Earth is not a perfect sphere but a spheroid, bulging out at the equator and a bit compressed at both poles. A spheroid can be defined using the lengths of semi-major and semi-minor axes and flattening factor. Semi-minor axis is the shortest radius of the spheroid, while semi-major axis is the longest radius of the spheroid. We use different spheroids to approximate Earth's shape. In this illustration, the red outline represents a cross-section of the Earth's surface and the white line represents a spheroid. In this case, the center of the spheroid is placed such that it does not coincide with the center of Earth's mass, but better fits the bottom right part of the cross-section. We call this positioning of the spheroid as local datum because it better fits only a part of the Earth and allows more accurate mapping of that part of the Earth. Hartebeestok 94 is an example of local datum of South Africa. Similarly, NAT 27 and NAT 83 are local datums for North America. Now, here is an example of a geocentric datum. In this case, the center of the spheroid coincides with the center of the Earth's mass. We also call it global datum because overall it better fits the globe. And WGS 84 is an example of the global datum. We use this when we work on a global data set. So to clarify, a spheroid approximates the shape of the Earth, while a datum defines the position of the spheroid relative to the center of the Earth. So, the choice of reference system or datum depends on the location of your interest. Here is a table that shows the spheroids and their properties used in 3 commonly used datums. In summary, a geographic coordinate system uses a 3-dimensional spherical surface to define locations on the Earth. In GIS, a point is located using longitude and latitude values. A datum provides a frame of reference for mapping locations on the surface of the Earth, and the choice of datum depends on the location of interest. This is all about geographic coordinate system. Hello, thank you. In this video, we will talk about how we can represent the 3-dimensional Earth surface into a flat surface. We know that the Earth is a spheroid, and we have already seen how to locate a point on Earth using longitude and latitude. Now we will learn how to represent the same point on the 2-dimensional surface such as map. This method also called as map projection. There are different ways to project the 3-dimensional Earth surface on a 2-dimensional map. When we project the Earth surface using a cylinder, we call it cylindrical projection. When we project the Earth's surface using a cone, we call it conical projection. When we project the same using a plane, we call it planar projection. In this lesson, we will focus on one type of cylindrical projection, universal transverse Mercator, also known as UTM, is an example of a cylindrical projection. Cylindrical projection is created by wrapping a cylinder around the globe and projecting the globe surface on the inside surface of the cylinder. It divides the Earth into 60 longitudinal zones. Here is an image that shows how these zones are divided. Each UTM zone is 6 degrees wide in longitude. Zone 1 starts at the international date line 180 degrees west and increases towards east. Also, at the equator, each UTM zone is further divided into northern and southern zone. So, a UTM zone is usually identified with a zone number and north-south. Example, Fairbanks, Alaska is in UTM zone 6 and the Cape Town in South Africa is in UTM zone 34 south. Now we will learn how to represent a point in the UTM projection system. In a UTM zone, the x-axis is called easting and the y-axis is called northing. The easting and northing values are in meters. In each zone, the central x-axis value, also called central meridian, is set at 500,000 meter easting and the y-axis value at the equator is set at 0 meter northing, because the easting length changes from the equator to poles due to Earth's curvature. In a UTM projection, a place is located using the easting and northing value in meters. The easting value is the distance of the place from the central meridian of the UTM zone, and the northing value is the distance of the place from the equator. Here is an example of how to represent the position of Fairbanks, Alaska and Cape Town, South Africa. In summary, map projection portrays the surface of the Earth on a 2-dimensional flat surface, example, a piece of paper or computer screen. And there are 60 UTM zones and a location is expressed in meters along with the zone number.